Hello and welcome to lecture 8. This is video 1 of machine learning from data, and in this lecture we are focusing on linear models. Now we have looked at linear models before, but now we will be able to use them as a modeling tool for regression and classification type problems. We'll also see if we are able to use them in other machine learning problems and how. So that's the focus of today's lecture. But now we have utilized a lot of like the previous lectures developing some theory, right? In some of the previous lectures, we discussed theory a lot, I would say, and essentially we wanted to establish some kind of feasibility in learning in the sense that we wanted to derive a relationship between E in and E out. And we were successfully, I would say, to a certain extent, able to do that. And in that process, first of all, we have this relationship between E in and E out. And in that process, we also figured a fundamental trade-off, right? So we saw a fundamental trade-off through the lens of two different analyses. The first one was the VC analysis, and the second one was the bias variance trade-off. Okay, so just to quickly review what the VC analysis kind of pointed versus what the bias variance analysis said, was that the VC analysis showed us that the choice of my hypothesis set needs to strike a balance between approximating F on the training data and generalizing on the unknown new data. So this was the approximation versus generalization. Approximation versus generalization trade-off. So what's going on in this trade-off? Well, if my hypothesis set is too simple, so maybe like a very low DVC somewhere here in this region, right? I will fail, maybe I will fail to approximate F well, right? And then I would like end up with a huge in sample error, which is this like blue line showing me E of n, right? Somewhere there. But if my hypothesis is too complex, somewhere here, so then of course I'll get a small in sample error because chances are high that I'm going to find my F or like something close to F, right? But then my model complexity went up here, right? And that contributed too much to my overall error, right? So this is the approximation generalization trade-off, which is presented in this picture right here. And we have to somehow come up with a hypothesis set that is able to balance these conflicting goals. And that's what this curve is doing. And we have something that's known as the optimal VC dimension. And we discussed that a lot and how that impacts complexity, how like there has to be that optimal point somewhere. And ideally speaking, that's what we are trying to get at, right? So we have to balance out the in-sample error and the model complexity to somehow get some reasonable out of sample error. Now, if you remember, the VC theory relied on some conditions, on some assumptions, and these assumptions, if violated, will make this entire thing go wild. So if it gets violated, you cannot be sure that this theory will hold or this like relationship will hold as such, right? So that's what the like some of these conditions tell us. You cannot look at your data before choosing H. Data must be generated independently, identically distributed. Basically, it should be IID from some distribution, and the data and test case should come from the same bin, right? So it should come from the same bin. Again, the same example, let's say election results, right? I cannot get the data, I cannot get the sample from, let's say, some other country if I'm trying to predict the election outcome in the United States. So that's what the idea is. So basically, the theory is going to fall apart if we don't follow those assumptions, essentially. Now, what's the advantage of the VC theory? The advantage is that it's completely general. It applies to any machine learning problem as long as these assumptions are not violated. Okay, so that was about the VC analysis. What about this bias variance trade-off? Well, this was another way to look at the same trade-off that's happening here, right? That's happening in the VC analysis, except that first of all, we were looking at the squared error cases here, right? This was VC analysis was more based off of like we were kind of restricting the derivation. I wouldn't say that it's only based on binary target functions, but and it can be, of course, extended to real valued functions. But the proofs become really technical and they do not add anything extra. So the insights are similar. So that's why Usually when we are dealing with squared error, with like real valued functions, usually we looked at the bias variance analysis. So that's what another reason why we looked at this. And then what happened? So, well, if there was a very simple hypothesis, let's say just like 1, and both the average function, remember we found g bar, right? The average function, um, and the final hypothesis would be like almost the same or like very close. So the variance was almost 0 in that situation, and bias depended only on how well the single hypothesis approximates the target function, right? And then there was another side to it. If let's say we have a very large model with like almost every possible hypothesis in it, so of course different data sets will lead to different hypotheses that will obviously be closer to agreeing with my target function, right? But the entire spread would be huge. And so what will happen is that although we will be able to reduce the bias, right, the variance is going to be large, right? And we kind of depicted that using this example here. So in this situation, when we were trying to use a very simple model, which was h of 0, right? And they were just like, essentially we're trying to find out what my EF out is going to be using the bias and the variance values, right? And so we found out in this case here, the variance, like in my simple hypothesis set, which was like just like a single line, right? And with no slope at all, we were able to see that my variance was really low and my bias was huge. But here in this case, although this was a complex model and we said that like if there were just like 2 points, we could literally make the line pass through those 2 points, but the variance was huge, and so the E out was humongous. And so I think a better model was the simpler model. And then we did a similar kind of an analysis for, I remember, with 5 points, and then we saw the results were different. So essentially the bias and the variance are components of my E out as shown here, but then it depends on the model complexity, it depends on the number of data points, and so on, right? So both of these are fundamental to any machine learning problem because they bring out that trade-off that always exists, and we as machine learning practitioners, we as data scientists are supposed to be aware of that and should try to solve any problem that we are working with, keeping this in mind. That's the whole point of this trade-off, whether you look at through the lens of the VC theory or you look at it through the lens of the bias variance analysis. Okay, so having said that, because we have this, let's keep it and let's remember this because this will come back. This VC analysis will come back in a short while. But then let's move on to something that we want to focus on in today's lecture. That's the linear model. And the way we are going to analyze this linear model in today's lecture is that we are going to look at 3 fundamental types of problems using our credit card analysis problem, or the credit analysis problem that we, I think, looked at in chapter 2, most likely. So let's look at these 3 types of problems. Now, the very first type of problem could be that an application comes in, right? And I have some information about the applicant, and I want to either deny or approve their application, right? So there are just like 2 outcomes here. And so this is something that's known as a classification type problem. And the second sort of possibility could be that, let's say I have all this data from like about an incoming applicant, and I just want to like kind of predict the amount of credit, some credit level for that applicant. So in that case, the outcome is going to be a real number, right? And so this is a regression type problem. So whenever the outcome, and this y is nothing but the outcome variable. So if the outcome variable is +1 or -1, just like some binary outcome, then that's a classification problem. If y belongs to like it's a real valued function or like variable, then it has a real value. It could have like any real number as the outcome. And that's a regression problem. For example, in the credit card analysis, I could do amount of credit. And then there is this third kind of problem where we are asking for the probability of default, right? So in this case, I'm interested in like what is the probability of customer A like defaulting, right? So maybe is it 0.4 or is it 0.9 or whatever, right? So the range of the values, because you know that the probability value cannot be less than 0 and cannot be more than 1. And so you know that my y is going to lie between 0 and 1, like within that range. So this is a third kind of problem that we are going to look at through the lens of the linear model, of course. And this pretty much sums up almost all important machine learning problems. And we'll see how using the linear model we can build and get more complex models as well. Okay, so why are we like focused so much on the linear models? And reason for that is that this is the most fundamental model. This is the most fundamental model that exists in machine learning, which means, what does this like fundamental means? Well, this means that pretty much every machine learning problem can be solved using my linear model. Well, so why is it fundamental? Well, on its own, it can solve a lot of problems. So on its own, it's able to solve most or many, I would say, ML problems. And if it's not in its existing, like in its current form, able to solve those problems, it is a building block for other models. So that's why it's fundamental. So it's a building block for other models. For example, the first model that comes to my mind is the famous neural network. You can think of a neural network as a more complex version of a linear model when you have like multiple linear models cascading. And that's the first example. The second example could be support vector machines. So neural networks, support vector machine, a more like, I would say, a robust linear model. And of course, we'll go into the details later. But then let us define, because it's such a fundamental model, let us define the linear model and how it begins. So if you recollect from, I think, chapter 2, lecture 2, the way it's defined is that it begins with a linear signal, right? So the way we defined it was W transpose X, where my W are the weights, right? So my W are the weights in a D plus 1 dimensional space. Why? Because there was that bias component that we talked about. And my X was this augmented by 1 always, again, because of the bias term. So where is the linearity here? And because we are calling this a signal, let me denote it by S. Okay. So first of all, it is definitely linear in X, like linear in variables, which is my linear in X. But when we are like thinking of this linear model in terms of the algorithms that are going to actually come up with the W values, right? We focus on the linearity of W. So it's also linear in weights, right? Because we're thinking in terms of developing some certain algorithms that are going to get my W. So that's why this is linear. And if you think about linear in X, this is pointing towards, like this, geometrically speaking, is nothing but the equation of a hyperplane, which in two dimension becomes a line. So essentially, like the linear model represents a line in a two-dimensional space. It's as simple as that. So it's really easy to interpret. On its own, it's able to solve most machine learning problems, and it's a basic building block for some of the very complex but widely used models. Okay, so having said that, as we said, is it like, so the question is it possible to solve any kind of machine learning problem using the linear model? So is it possible to solve any kind of problem using a linear model? Well, a short and quick answer to that question is yes, because as I said, this is one of the most fundamental models, and the machine learning problems can be categorized into these three huge categories that we just looked at here, right? So we can map this linear model to solving each of those problems in a certain way. And that mapping essentially involves transformation. So we can take the linear signal the way it is here, S equals W transpose X, and then transform it to answer like more or less answer each of these three types of problems. These like most basic and I would say most exhaustive list of all problems that exist in the machine learning field. So let's look at that. How does that happen? So my linear signal is W transpose X. Let me write it down. We can transform this linear signal. How do we transform that? The first problem is the classification problem. So if we are going to transform this, because this is going to be some real valued, real value, right? So what we are going to do is, in case of classification problems, I can use a sine function, right? And how does it look like? If we just draw a simple so this is -1 plus 1. So we can make this linear signal pass through that sine function such that my final hypothesis set is going to be denoted by sine of this linear signal, which is W transpose X. So this is sine function for classification. Okay, the second type of problem was regression. So this is known as identity transformation. Essentially, we take the real value as it is. So we can do an identity transform or transformation. What it looks like is nothing but my h is going to be my s. Just take it as a real valued function. So essentially, my h of x is going to be the direct W transpose X. Right. So that's how I'll solve regression type problems using this linear model. And then the third one is the probability type problems. We can use something that's known as a sigmoid. So what is this sigmoid function? Well, it transforms and it's like a smooth function, and it exists like, it has this like S-shaped curve that exists only between 0 and 1. So these are the range of values. And so if we denote this curve by some theta, then you can say h equals theta times theta of s, not times, but of s. So essentially h of x is going to be theta of this linear signal. So in this, and this is later on will be called logistic regression. So I'm just like writing that probability type problems essentially. So all three major types of machine learning problems can be solved using this linear signal and transforming it, which is why this linear model is so fundamental. So having categorized this linear signal into three major categories will help us further analyze each of these in sufficient detail. So I'm going to do that starting from the next video, in which I'll talk about classification.